This is topic 2.5, exponential function context and data modeling. So starting at the top, it says sometimes data from an exponential function does not display proportional growth pattern. This is due to a vertical translation of the function. So vertical translation meaning you're adding or subtracting some kind of constant to your function there. Okay, or in this case, because it's exponential, a times b to the x, whatever it may be, and then plus a constant there. However, if we can add or subtract a constant from the output values to reveal a proportional growth pattern, then the initial function was also exponential. So if we take the output values and add a constant, we can show proportional growth. Then we also know that we have an exponential function. So example number 1, it says selected values from exponential functions are given in tables below. For each, find the constant value that can be added or subtracted to the output values. So what they're asking us is this: what do I add or subtract to these output values to reveal a proportional growth pattern? So we have to change the output somewhat. Then write an equation to model the function. So for example, if we take a look at A, if I wanted to check whether or not that this is an exponential function, I would check the ratio of my outputs. And what I notice is that the outputs are not proportional. So therefore, I'm not dealing with something right now as it is. However, as I start taking a look at the data, this is plus 6, this is plus 12, this is plus 24. So what you're noticing is it is doubling, and then now I add a 48, so it's doubling again. So what happens is these outputs, 12 over 6, 24 over 12, 48 over 24, it's showing some signs of being proportional. So now what I have to do is I have to ask myself, what do I add or subtract to these outputs so that they become proportional? So what we are seeing here is this: the 7 and 13 are really close to 2, and the 13 and 25, their ratio is really close to 2. So what I have to consider here is this: what if I took my output values and I used a constant and subtracted 1 from them? So what happens is 7 minus 1 is 6, 13 minus 1 is 12, 24, 48, 96. So now I do have a ratio of output values that are proportional, and they all have a proportion of 2. So therefore, f of x minus 1 is equal to, and what I have here, my initial value is 6 times 2 to the x power, okay, because the proportion is doubling. So if I add 1 to the other side, what I'm looking at is 6 times 2 to the x and then plus 1. All I did was add 1 to the other side, and so that would be my equation there. Okay, for letter B, same thing. So 10 divided by 2 as proportional is not the same thing as 34 over 10 and so forth. So we're following the same idea. So what I do notice is this is plus 8, and then this is plus 24, and this is plus 72. So what I'm noticing here is everything is tripling in its size. So because it's tripling in its size, I have to find things that are multiples of 3. So in this case, because they're multiplying by 3, if I add 2 to my output values, 2 plus 2 is 4, 10 plus 2 is 12, 34 plus 2 is 36, I have 108, and I have 324. So what you'll notice is that's 3, this proportion is 3, this proportion is 3, and then 324 over 108, that's also going to be 3. So I took my output values and I added 2 to them. The initial value is 4, and it is being multiplied by a ratio of 3. So now when I subtract the 2 to the other side of the equation, I have 4 times 3 to the x minus 2. By the way, just so in case you're wondering, the 6 is where I got the 6 from, the 4 is where I get the 4 from, and the ratio is where the 2 comes from. The ratio here is where the 3 comes from as well. So just to kind of help you identify where I'm getting these numbers from. Okay, and then the third one, letter C. So what you're noticing is it's getting smaller. Okay, so because it's getting smaller, I'm thinking that I have to be able to cut it down. So if I were to add 1, what you'll notice here is, again, 32, 16. I'm now creating multiples of 2 again, powers of 2. So 32 over 64, 16 over 32 is a half, 8 over 16 is a half, 4 over 8 is 1/2 as well. So I took my outputs and added 1 to it. My initial value was 64, and it is a decay. So h of x is equal to 64 times 1/2 to the x power minus 1. And that would be my function there. Okay, so that's what I'm looking for. And that is, again, we are adding or subtracting a constant. So constant value that can be added or subtracted to the output values. That's this right here in yellow. That's what we were doing. We're adding and subtracting values to reveal a proportional growth pattern. That's what we were doing on these pieces right here. These are the proportional growth patterns. Okay, so that's example number 1. Example number 2, an exponential function contains input-output pairs of 0, 7 and 3, 137. The function has the form g of x equals 5 times b to the x plus d, where b is the base, d is the constant. Write the 2 equations that can be used to find the values. So what you have is an input value, x, and then you have an output value, which is g of x. So I'm just going to use those input and output values to make my 2 equations. So I put in 7 for g of x. I get out 7 when x is 0. And then the second equation is using the 3 and the 137. 137 is equal to 5 times b cubed plus d. Okay? For letter B, find the value of b and d. So the first thing I'm going to do is use the fact that b of 0, b to the 0 power is 1. So that means that this is just 5 times 1 plus d. So I subtract the 5 to the other side, and I get d is equal to 2. Once I know that d is equal to 2, I will substitute it in to my second equation. So I put the plus 2 there. And because I have to solve for b, I'm going to undo everything. So I'm going to subtract the 2 to the other side. I need to get rid of the 5, so I'm going to divide by that. So b cubed is equal to 27. And then I have 2 choices. I can either cube root it. So when I cube root it, I look at the cube root of 27. Or I can just rewrite 27 as a power of 3, which is 3 to the 3rd power. So therefore, once the exponents match, that means that b is equal to 3. Or the cube root of 27 is 3. So once I know this, I can rewrite my function. G of x is equal to 5 times 3 to the x plus 2, because I solved for b and I solved for d. Okay, turn the page. Okay, so the number of bacteria growing in an incubation culture doubles every day. So what that means is it's going to increase by 100% if it's doubling. So that means that my base value is going to be 2. And the reason why is because it's 1 plus 1. The 100% converted to a decimal is 1. There were initially 920 bacteria, so this is my initial amount. This is what I need to know. Okay, so that means that A is equal to 920. And so let B be the number of bacteria and T is the time in days. So once I know this, the first thing I want to do is I want to write an exponential expression for the function model. So what that tells me is the number of bacteria after T days is equal to 920, the initial amount, times 2, because it's doubling, to the T power. And that will be my exponential function. Letter B, find the number of bacteria when T is 5. So I want to figure out what B of 5 is. So I'll do 920 times 2 to the 5th power. And so therefore B of 5, if you use your calculator, is 29,440 bacteria. Okay. Letter C, when will the number of bacteria reach 10,000? So what that's telling me is I know that the bacteria is 10,920 times 2 to the t power. Okay, so I have an exponential equation. I'm going to divide by 920. So I have 2 to the t power is equal to 10,000 over 920. Okay, I need to solve. So in order to bring t down, I can do log base 2, or what I can do here is I can just convert it into its logarithmic form. Okay, so the base is 2, so I have log base 2. The exponent is t, so I'm going to bring the t to the other side, is equal to 10,000 over 920. Okay, once you're here, I can do log base 2 of 10,000 minus log base 2 of 920. Okay, or we could do change of base formula, right? So this would be log of 10,000 over log of 2 minus log of 920 divided by log of 2. So again, using your calculator, you're just going to have to round it to the nearest 4 decimal spaces. So this is approximate 3.442. I got to check my calculator one more time for the 4th decimal space. But that's what we're going to be doing there. Okay, letter D, write an exponential expression to indicate how the number of bacteria increases every week. Okay, so what that just means here is this. I have B of t, and it's 920 times 2 to the 7th power t. Okay, so if I use my power property, 920 times 2 to the 7t, because power means that you are going to multiply. Okay, and then the last, find the number of bacteria in 2 weeks. So number of bacteria in 2 weeks, 920 times 2 to the 14th power, because that means that t was equal to 2 in this case. And so therefore, we're looking at 15,073,280 bacteria. Okay, so that's how we would be using our equations. Also, I just want to point this out. If you have a graphing calculator and this was a calculator function when you had to solve letter C, what you could do is set the left side of the equation equal to 0, and you set the right side of the equation not equal to 0, equal to y. And what happens here is if you graph both of these, here's 10,000. You're going to get a horizontal line like this. 920 times 2 to the t power is going to be some kind of exponential growth function. All you have to do is find the point at which they intersect. And if you find that point of intersection, that's where you can find your solution as well. And this works for any equation. If you graph the left side and graph the right side, find the point of intersection and you're good. Okay, so for this next one, this is very similar to the previous problem in number 2. An exponential function can be constructed either if you're given the common ratio and the initial value, or 2 input-output pairs. Okay, so we can find the initial value and the base ratio or common ratio with the 2 pairs. So let's pause here. Let's have you guys try out example number 4. And then you can take a peek at how to use the regression model for number 5. If you have a NumWorks, same thing. Just put in your data and then try it out. If you're doing the TI-84, the only difference between the linear regression and the exponential regression is when you go to calculate, you're not doing the linear regression anymore. You're going to look for exponential regression. It's the same thing, and then again, it's just a matter of following your 4 decimal spaces to create your function. Okay, so just put in your data and then see what you get out for an example number 5. Okay, so let's pause here. Let's give it a try. Give number 4 and number 5 a try, and then we will go through it together. Okay, so let's go through example number 4. So it says for for t values between 0 and 30 minutes, the number of fans inside a large sports stadium can be modeled by an exponential function f of t equals a times b to the t power, where f represents the number of fans t minutes after the door is open. So there are 47 people in the stadium 2 minutes after the door opens. So what that tells me is after 2 minutes, there are 47 fans. And then after 20 minutes, there are 2,602 fans. Use the given data to write two equations that's being used to find the values for constants a and b in the expression. So my function here, a times b to the t. So my first value is t. My second value is f of t. T and f of t. So 47 equals a times b squared. And then the second one, 2,602, is equal times a times b to the 20th power. And that's all they're asking for. It just says write two equations. So that's what I did. Here's one equation, and here's the second equation. It doesn't say solve. It just says write the equation. Okay, turning the page. We were going to use an exponential regression model. So if you use your TI, you should be able to calculate example 5B. So just starting with 5A. Use given data to write two equations. So again, write two equations that can be used to find the values of constants a and b. So we have g of x equals a times b to the x. So 21.54 is equal to a times b cubed. And then also 3.62 is equal to a times b to the 8th power. Now, using my calculator, I just punch those two sets of information into my list, and then I calculate the exponential regression. So the instructions are here for the TI-84s. If you have a numworks, be careful, because when you go to your regression, there are two exponentials, and as you look at it, when you highlight it, the first exponential is a times e to the bx. The second one is a times b to the x. So I'm going to choose the second one, a times b to the x. And then so once I select that and I go to my regression, I will also see it. So what I notice here is that my a value is going to be 62.8012. And then my b value my b value is 0.6999 . Okay, and so it just continues off. So I just cut it off to 4 decimal spaces there. So that's how I would do example number 5. Okay, at the bottom of this page, it's just a reminder, the graph of e to the x. This is kind of, it is an exponential growth function because the base is larger than 1. So as x gets larger, increases without bound, your output values also will increase without bound. And the reason why it's a growth is because e is an approximate value of 2.72 or 2.718. Okay, so the natural number e is used as the base in exponential functions that model contextual scenarios. So as we turn the page, example number 6. Okay, so example number 6, the number of bacteria B in a particular culture can be modeled by an exponential function. B of t equals 17e to the 0.31 t, where t is measured in hours. So what we have here, a of t is equal to a times b to the t. So notice if you have a numworks, these are the two different exponentials, with one with base e and one without. So a of t is an equivalent expression for b of t. So what that means is if they are equivalent, a of 0 should be the same as b of 0. So I want to find the value of b. Okay, and the b that we are referring to is this value right there. I'm sorry, I think it's a typo. We want to find the value of a, not b. Okay, so what we're going to do here is we're going to let t equal 0. So a times b to the 0 power is equal to 17 times e to the 0.31 times 0. So b to the 0 power is 1, so that leaves me with a. E to the 0 power is 1, so that's how I know that a is 17. Okay, if I needed to, I could fill it in. A of t is equal to 17 times b to the t power. Okay, and then that would be my function there to start off with. Letter B, find the average rate of change. So here we are talking about average rate of change again. So average rate of change from t equals 1 to 7. So if I want to find the average rate of change, that means I want to find b of 7 minus b of 1 over 7 minus 1. So what you're going to have to do is you're going to have to substitute the 7 in. So 17 times e to the 0.31 times 7 minus 17 times e to the 0.31 times 1. And then we're going to divide that by 6. So using our calculator, we're going to just truncate it 4 decimal spaces. So it's approximately 20.9521. For letter C, find the number of bacteria predicted by the model after 15 hours. So what's going to happen here is this. I have 17 times e to the 0.31 times 15. Okay, so again, it's just a matter of using your calculator. So I'm going to turn the calculator, calculation. So I have 17 times e to the 0.31 times 15. So I'm looking at approximately 1,777.9447. Okay, and so that would be it. For example, number 7, 50 deer were introduced to a large wooded area. So this is your initial value. The population can be modeled by an exponential function, a times b to the t. T represents number of years, and it increases by 13%. So what that means is my rate is 0.13, and so I'm going to increase. So that means my base is 1.13. So find the values of a and b. Use these values to write an expression for d of t. So I have d of t is equal to my initial value, 50, times 1.13, an increase of 13% to the t power. For letter D, according to the model, what is the population after 6 years? So we want to find what d of 6 is. So 50 times 1.13 to the 6th power. So if I do that correctly, it's 104.09. Let me see, double check here. 50 times 1.13 to the 6th power, 104.0975. Okay, and then so that's approximately 104 deer. For letter C, find an equivalent expression where d of t is measured in months instead of years. So in months, there are 12 months per year. So that means that d of t is going to be equal to 50 times 1.13. So it happens every 12 months. So I would just call it t over 12. Because if t was 12, 12 months means 1 year, it's going to increase by 13%, and then so forth from there. Okay? So that is it for section 2.5. Hopefully we have a good understanding on how to use our calculator, how to set up equations to find a and b values also.